Okay, good morning. We will start with the colloquium. This will be the 5th colloquium in the series of this season. And today we have two very distinguished speakers. So I will first introduce both of them, and then they will speak in the same order that I will introduce them. So the first speaker is Professor Paolo Giubellino. He is an experimental physicist working on high-energy nuclear collisions. After 6 years leading the CERN ALICE experiment, he is since 2017 a scientific managing director of the JSI Helmholtz Center for Heavy Ion Research, so-called JSI, and of the FAIR International Laboratory. This is the facility for antiproton and ion research in Europe, which is located in Darmstadt, Germany, and he is a full professor at Technische Universität Darmstadt. He is the author of over 500 scientific papers. He received several recognitions, among which 2 Doctor Honoris Causa, the title of Commendatore for Scientific Merits, the Medal of the Mexican Physical Society, the Fermi Prize, which is the highest recognition of the Italian Physical Society, and the Meitner Prize, which is the highest recognition of the European Physical Society for Nuclear Physics. And the second speaker will be Mr. Joerg Blaurock. He is the first joint technical managing director of the JSI Helmholtz Center and of the FAIR since February 2016. He studied mechanical engineering in Hamburg during his career as an officer in the German armed forces, where he worked until 1994. He went on to work for large-scale plant construction firms UHDE and Lurgi in the turnkey production of petrochemical industrial plants at various international locations. In 2007, he joined Alstom, which is today General Electric, where he worked in a number of positions, most recently for General Electric Deutschland. There, as managing director, he was responsible for the turnkey delivery of utility steam generators for electricity generating fossil fuel power stations. So they will present us the talk, which is titled FAIR. This is the title of the abbreviation of this new being built lab, the universe in the lab. So I invite Professor Giubellino to start.
Okay, thank you very much for the introduction, and thank you for being here. It's a great pleasure. I mean, I've worked along my long life many times with scientists from Slovenia, especially during my long years at the European Center for Nuclear Research. And I hope we can convey a little bit of the feeling for this new laboratory which we are building. So I will give you a bit more of the scientific part, and then you will see from Joerg how we are actually building it. It's a great moment for science because there's been some fantastic advances in recent times that have involved what in some sense is our combined understanding of the universe from observations out in space, which we now do in multi-messenger mode. We observe cosmic rays, we observe light coming from various sources, we observe gravitational waves. So we have a number of windows of neutrino astronomy, so we have a whole range of observables. But you know that most of what's going on up there is actually nuclear processes. From the very start of the burning of our sun, what moves the universe is nuclear physics. And if we want to understand what is happening up there, you need to perform experiments that allows you to provide you with a controlled environment where you can reproduce the processes which are happening up there, and you can then connect the Earth observation with the observation in the sky, the two through a lot of simulation and also a lot of analysis of huge amounts of data. Both these experiments and these experiments produce enormous amounts of data, and therefore are motors of development of computer technology, information technology, new algorithmics, things from the big data to real-time analysis, from artificial intelligence to quantum computing. They all play a role in our ability to tackle the enormous and complex amounts of data and the simulation of what is happening in these two other corners of the triangle. So what are we building? We are building an enormous facility which consists of accelerators, of a system which is called a superfragment separator, which allows to produce secondary beams and select very specific types of nuclei to do further experimentation, and storage rings, which were essential for measurements on more sophisticated measurements on these exotic beams that one can produce, and or to collect, cool, and then use antiprotons as a tool of understanding of matter. Why is this? So this is an S3 landmark. It's been repeatedly indicated by the European nuclear physics community in its long-range plans as its top priority. And it is an international organization which involves, of course, Germany as a main stakeholder because it's the host country, but then several other members. And we are proud of the fact that Slovenia is among the full members of the, and we will see what that means in a little bit later. Why is this happening in Darmstadt and not somewhere else? Well, because in Darmstadt sits a research center which is called JSI, which means Research Center for Science with Heavy Ions, that for more than 50 years has been doing research. It's a large institute. It's 1,500 people, so it's a big scientific institute. It's one of the biggest in the world in nuclear physics, and has made lots of important discoveries. If you look at the table of the elements, you see on the line 6 elements which have been discovered in this laboratory. And since the discoverers have the privilege to give the name, we have actually a Darmstadtium and a Hassium from the state of Hessen where we are. So we are very proud that we could give the name of our city to an element. But also, if you look, this is the table of the isotopes, number of neutrons versus number of protons. And the black ones are the stable ones, so the further you go away from the stable ones, the more recent is the discovery on average. And you see that once you get near the edges, lots of red dots, and those are the ones discovered at JSI. So you see that actually the vast majority of the recent discoveries of new isotopes have been done at JSI. We'll end up falling from this. And but also, we are very proud of the fact that by mission, and this I was telling to some colleagues a moment ago, while I was at CERN, we had a very strongly focused program. You do high energy physics, highest possible energies, the smallest possible scales. And then there are, of course, applications. Here, we have as a mission a very broad program, which we will see later includes material science, includes biophysics, therapy, atomic physics, plasma physics. It's a very broad program. And this is a fundamental difference between the two laboratories, which come from one and now have been for 5 years in the other, appreciate a lot. I mean, there is a very diverse culture and diverse scientific environment at GSI. One of the things we are most proud of is the development of nuclear beams for therapy of cancer. This was a major breakthrough that was first done actually on campus. We treated 440 patients on campus, and then went on for the first clinical center in Heidelberg was actually built by our accelerator team. The first person in charge of the accelerators is the person which now is responsible for the operation of our accelerators. And then went on, and now there are a number of those in the world, you all know why this is very important. Because if you destroy cancerous cells with a beam of photons, and you look at the depth in your body and where the energy is deposited, you see that actually the deposit is higher on the healthy tissue than the deposit that you can get in the cancerous cells. With a beam of ions, you can actually tune the energy, so the depth of the Bragg peak, so that you can have most of the energy actually deposited in the tumor and not in the healthy tissue. This is, of course, complicated, but when the tumor is located in a particularly sensitive area, tumor of the eye, tumor of the brain, tumor of the spinal cord, then you want to make all possible efforts to spare the healthy tissues around. And so this is really a winning technique. With the years, this technology has been developing, and there are still subject of extensive research or vigorous research, because there's many things that you can still do. One, and you will see it later because it involves a joint project with, in which Slovenian scientists have an important role. One of the challenges are moving targets. If you have a tumor in a lung, the tumor moves, and so it will lose any interest to have a very high precision tool if the target moves in front of it. So you have to find a smart way to adjust to the movement of your target. But there's also there's very many development projects, and I will only mention a couple, but there are development projects which involve immunology, but one of the interesting one is the fact that you can think of using, what are you doing with this beam? You are actually destroying cells in a specific point. So basically, you have, like in a science fiction movie, a scalpel which can cut in a well-defined position inside the body without opening it. So one of the things that you can think of is, for example, can I do a heart surgery with a beam of particles? Can I do an ablation? The answer is yes. The answer is yes, and we actually have tried this with pigs a few years ago. This was being published, and it worked very well. So it is now starting to move towards the clinics. I think there's been in the world only 2 or 3 patients so far, people that had no other possibility of treatment. For the moment, it's in this category in which you only do it if there's no other solution, but so far it has worked. So you can actually use a beam as a remote scalpel, pretty much like in a science movie. But as I was saying before, a lot of developments involve computing, involve the software, involve the algorithmics, and involves also, as you can imagine, if you have large amounts of computing, you have an issue of power consumption. You all know that, the power you use to power the computers, you cannot save. Although you can save a little bit with some smart schemes, but what you can save is the power you have to spend to cool them. And this is the thing with which we have invested a lot in the development, and I must say this is one of the most advanced systems in the world from the point of view of energy efficiency. To give you a number, typical computer centers spend in total 1.3 times the energy they spend for the powering of the computers. So this is the additional one. Here is 1.07. So the additional power compared to the one that is needed really to power the computers is reduced dramatically. If you have a large system, that really makes a difference. And especially with the current energy prices, this becomes an important. So much that we got a certification, the Blaurock, as one of the leading technology structure for sustainability, energy saving, and we call it a Green IT Cube. But the other thing that is extremely important to us is the fact that we are a talent factory. We are a center which has among its fundamental missions to provide opportunities for young people to develop, to find opportunities for their careers, to get training at all levels. We have from the summer student program, that is a 8-week stay in the summer, to stages which are done under the so-called Get Involved program that is run by, so if any one of the young people wants to know more, Pradeep Ghosh left is sitting there, is the one in charge of this program of fellowships for young people. We have more than 300 graduate students, which is a very large number. I mean, I think that if you compare with typical university sizes, this is really a large number of graduate students. And we have continued development of bilateral agreements with universities and institutes around the world to foster the exchange and to foster the possibility for young people to come and get training and then go back to their home institutions. The 3 latest have been with the Slovenian institutions, but also another would be in the MITAC, which is a pan-Canadian organization with the University of Halifax, also in Canada. And so this was the last 3 months. And these things continue to, immediately before was Krakow and so on. There's a continuous process of new bilateral agreements, and I hope that we will continue developing the relationship with Slovenian institutions. So this is a schematic view. This is JSI, this historic laboratory I was telling you about, with its linear accelerator and this synchrotron and then storage rings. This is FAIR, which is under construction, and you can recognize the big accelerator in the corner here that was upright also in the photograph before. Notice that although this is under existing and this is under construction, from the operational point of view, this is one center. This is not by chance that both of us, we are director of both, because it's an integrated system of tools for research that works all together. What makes us special? And this is important, in my opinion, to just stress, because especially young people, you have seen millions of pictures of accelerator laboratories. You have these round circles and you say, okay, they all look the same. No, they are not the same. They are very, very, very different, because you have to optimize your tool to what you want to do. They are all, in some sense, microscopes. They are a way in which you access the structure of matter at the small scale. They are the most powerful microscopes we have. But then your microscope can have very different optimizations. In particular, the 2 big families are the family like the CERN ones, which go to higher and higher energy, which means the smaller and smaller scales. And ours, that goes for intensity, I mean, more and more particles in your beams, and more precision, that then you exploit using the storage rings, where you then do precision measurements. To give you a simple example, I have an extremely rare isotope, for example, that plays an important role in stellar evolution. Then I can produce it by accelerating nuclei here and then hitting a target and then selecting with this very complex so-called fragment separator. Then I can collect them in a storage ring, and then I can do measurements with them. And we are capable to measure individual nuclei. We have one nucleus in a ring, and we can observe a transition to a different state of this nucleus individually. So you can imagine that you can take a single nucleus and look at it and see what it does. And maybe though you needed to produce billions of particles in order to be able to select that one rare one there. Why is intensity crucial? In accelerator lingo, I'm sure you've seen this in many papers. So if you've seen papers on particle physics or nuclear physics, the parameter is actually called the luminosity. And it's not by chance that you call it luminosity, because in practical terms, sorry for those who are specialists, this is a very simplified example, but I think it gives you the idea of what we are doing compared to what others are doing. Our knowledge is acquired through simple experiments like this. I have a source of photons up there. The photons interact with a target, which is this object, and I detect with my detector here the results of the interaction. I process it here, and from the processing of this data, I reconstruct what I'm looking at. This is a process that we all do automatically every day without realizing, but this is what we are doing. We're doing a photon scattering experiment on a target with a detector and then a processing center. If I want to see more details, then I have really two ways. I can go to higher energy projectiles, and then I do an X-ray of this object, for example. Higher energy, shorter wavelength, go to X-rays, then to go to gamma rays, and then higher and higher, and I will start looking at individual nuclei, and then quarks, and then so on and so forth. Or I want to actually look at collective properties then I want to have more light, more luminosity. So I will have to crank up the light in the room if it was darkish and increase the intensity of my beams. And that's what I need to do. And these two things are generally very different optimizations of the accelerators. If you would look at the operation diagram of this, oops, let's make a light. It go off. Anyway, of that synchrotron up there, you would see that you very quickly accelerate, throw out the particles, go down, then accelerate again, then go down, do accelerate again. So you have like a continuous train of cycles of up, down, up, down, up, down. So your magnets are under enormous stress because they continuously ramp very fast to maximum, and then down, and then up, and then down. If you look at the LHC, you will see a very slow ramp, and then it stays at a certain energy for a long time. So you accelerate, take your time, and then for hours, you keep the thing circulating, colliding with the opposite beam, and then you go down again. So you go to much higher energy, but you then stay there. Instead here you do tum, 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 like. So it's a completely different technology. You have completely different developments. So Heinrich said that this is our family, and our family consists of a number of countries which own the center, and there are the orange ones that are the so-called shareholders. And this is a GmbH, it's a stock company. So these countries are actually owners of the centers. So in particular, Slovenia.
Good point.
Yeah, thanks. So I split the two functions. So Slovenia is actually an owner of this laboratory. You can think that your institute has a dependent laboratory on German soil, which is owned by Slovenia. This is very important because it is not just a participation; it's really legally a direct ownership. As you can see, Russia is also a a shareholder, and this is now, of course, under debate. What is the fate of the Russian contribution because of the events that we all are aware of. This tomorrow we run away very early because we have an extraordinary meeting exactly to decide how to proceed. But at the moment we are freezing our collaboration with all Russian institutions because of the war situation, which is very unfortunate for science. This is really a terrible moment. I mean, science is built on international cooperation, is built on, you can see the whole world working together, but we are in front of very exceptional circumstances, and we have to take exceptional measures. So this is how things are. But you see, these are the countries which own the center, and the blue ones are countries on the opposite which participate in the experiments, and it's about, the scientists are about 3,000. An important point is that the countries which are owners, co-owners and members typically contribute not so much in money, but they contribute via involving the national industry in their building components of the accelerators. I must say, in this sense, Slovenia has been probably the most efficient country, because they basically, thanks to the availability of a team of companies that produce high-tech components in terms of, especially of controls of accelerators and other machinery, has been able to really fully transform its contribution into benefit for the national production in the country. So basically not a euro is leaving Slovenia, it goes to Slovenian institutions and companies that produce elements for the accelerator. So you really see three pillars that you have a scientific program, the involvement of scientists that we hope will grow progressively in time, involving also, say, not only nuclear physics, but also other areas. The accelerator technologies, in particular with this strong involvement of the companies like COSI Lab and Instrumentation Technologies. But also, as I said before, the third pillar of our activity is education and growth of talent, and so that we develop progressively the exchange, especially for young people. So, I have to split things. So this is, in a short summary, the characteristic. It's the activity done by the Slovenian companies is actually ubiquitous. It goes in practically all of our accelerators. So it's really not focalized to one thing. It happens a bit everywhere, and this is very important. But also, it's important that we'll see in a moment what phase 0 means. But the phase 0 is a program which is already ongoing and which sees already this involvement. So what do we do scientifically? So we want to find answers to fundamental questions about the universe. And we do that by reproducing in the laboratory the conditions in which these processes take place in different moments of the universe expansion and evolution. Some of these questions that we want to answer: where are the heavy elements, gold, platinum, created in the universe? They're actually created in very particular violent events, like the mergers of neutron stars, where in this specific case, the triangulation with the observation of visible light and of gravitational waves is particularly strong. We'll see it in a second. What happens at the interior of these neutron stars? But also planetary science. Planetary science is a fascinating field. We know actually very little about the interior of planets. Even our own Earth, beneath our feet. It's actually poorly known what happens inside. But we can reproduce these conditions, which are very extremely high densities, and then study them with dedicated tools in the laboratory. But also, we are, for example, the laboratory which ESA, the European Space Agency, has chosen as its counterpart for radiation studies in the laboratory, which are now very hot topic, because you all know that the current frontier for space is long trips, Mars, colonies. Now, this is not trivial, because instrumentation and humans are exposed to very high radiation dose. If you have a trip to Mars and you do nothing, your crew, each individual in your crew will have 10 to 20% probability to have developed a cancer on the way. There is a high probability of developing cataract. There is a whole family of diseases that one has to then study and prevent and mitigate these risks. And that's what we study in the laboratory together with ESA. But also things like, where does life come from? We have possibility to simulate. Both of these are together because they rely on the capability that we have to produce, to resimulate the spectrum of the cosmic radiation with high accuracy. And then one other thing that you want to study is how do you create complex molecules on grain of interstellar dust. And that actually is one of the things that are being done. And as a corollary to this, a lot of applications. Again, we talked about performance computing, but we talk about developments in biophysics. I told you about some new concepts of therapy. Another new concept of therapy is the so-called flash. It's an ultra-fast, high-dose irradiation that seems to have a considerable advantage in sparing, again, the healthy tissues in compared to a long irradiation. But also research on vaccines, for example. We have a collaboration with the German Center for Infectious Diseases. In developing vaccines, one of the issues is how do you deactivate a virus? Apparently, that's one of the things we are studying, if you do it with a beam, you will preserve much better the surface of the virus, so it is actually a better tool for the development of vaccines. I'm using too much time. I don't know how much time I have been speaking. I try to hurry up. Now. I was telling you how these things the various things come together. You all have heard about this fantastic result of our friends from gravitational waves that have observed a neutron-star merger, and then coupled to that has been the observation of light emitted by the after processing in creation of elements. Now, this is the light observation. The red points are the observations, and the blue line, when they came out, is a prediction from 2010 by a group of scientists that actually happened to be from our laboratory. So why a group of scientists from our laboratory was calculating what would be the light emission after a neutron-star merger? Because this is one of the key measurements that one can do at FAIR. Why? Because when you have a collision of nuclei at our range of energies, you can reproduce by tuning the energy either the structure of matter in a neutron star or the structure of matter in a neutron star merger, which is going to be higher density. So you can understand the starting conditions, and then you can actually do the fundamental measurements. When you have a merger, you don't produce the elements as they are. You produce very exotic neutron-rich elements. You start from a neutron star, so it's quite natural. And then they will decay to the ordinary elements as we know them. all of these processes we can actually then do in the laboratory in different experiments. And but many others. There was in 1983, Fowler indicated as one of the most interesting things to be measured to measure the origin of the building blocks of life, carbon and oxygen. Carbon and oxygen are produced in the late phases of evolution of heavy stars. By, you first make helium, then you put 3 heliums together, you make carbon plus helium, you make oxygen. How much carbon, how much oxygen depends on the cross-sections of these processes, which are very poorly known. But you can measure them experimentally, and that's what we are doing. 40 years later, we finally are getting to give numbers on these. And so on. I told you about the interior of the planets. What is our special weapon here is the fact that we have one of the few petawatt lasers and one of the that we can use together with a beam of particles. I told you about the grains. I don't tell you more. So our science program is structured in so-called 4 pillars that are the hadron structure, the nuclear structure, nuclear astrophysics, the study of the phase diagram of strongly interacting matter, and then atomic physics, biophysics, plasma physics, and material research. These are our fundamental subjects that we will do in dedicated experimental areas. For example, these are the dedicated experimental areas for the programs of atomic physics, plasma physics, materials, and biophysics. And these are for nuclear structure and nuclear astrophysics. I told you we do have this special system to select out of the very many isotopes that you produce in a collision, exactly the one we want to study. And we have scientists from Slovenia that are involved in particular in the NUSTAR physics, so as you said, nuclear astrophysics and nuclear structure in the programs high spec. So these are names that will tell you nothing, so let's stay with nuclear astrophysics and nuclear structure. And in the biophysics, although we hope that progressively also other of the fields of research will get involvement. And the one important aspect of this is the fact that these scientists are participating already to the scientific program that is happening now. And these are some components which are developed here and that are therefore well known to the locals. And it is important to say in these projects there is a very strong interplay between what happens in the host laboratory and what happens in the various laboratories. It's not that one simply sends people over. The components of the experiments are developed, designed, and conceived and constructed in the home laboratories and then brought together with the ones designed by others. The science programs are conceived in the different laboratories and then discussed with people coming from the others and put together. And so there is this continuous back and forth between a global picture worldwide and the local reality of each individual participating laboratory. And this is what makes this so fertile for the laboratories which participate, because it's not like just shipping things and people, it is developing here and conceiving things here and then putting them together. So this for NUSTAR, and this for the, I told you before, in the particle therapy, there is an important collaboration with COSI Lab from Slovenia for moving targets for tumors in the lung in particular. When will we start? We'll start 2025, 26 or so. So what do we do until then? Until then, we have the upgraded accelerators of the JSI Center together with the new detectors and experimental apparatus which have been developed for FAIR. You put the two together and you have what is called FAIR Phase 0, which already since 2019 is in operation and allows students and researchers from the laboratories which are participating in the future FAIR program to have today a scientific output, to have today results and the possibilities to work together. And there are many, many results which are coming up. These are, for example, results that I was telling you, results from biophysics, results from material science. We have developed sensors for viruses based on the construction of nanopores so this is our nanotechnology department, which works with American groups to develop sensors for viruses, which are passive sensors, so very handy, and we don't need reagents, and also allows young people to come and start working and start developing their activity. Students from here, you can recognize the professor, but also the young people which have been in the laboratory during this last year's experimental campaign, and now we continue with more. So this is also getting formalized. We had a meeting with the Slovenian authorities, and in particular from the Josef Stefan Institute in November, so quite recently. Actually, this meeting now is a little bit the delayed version of aspect of this meeting because COVID blocked us. But in which we really looked at the various aspects, the knowledge development, the educational aspects, and the industry technology development aspects, which in Slovenia are particularly well coordinated. And we signed some further agreements in this Get Involved partnerships that will allow more and more students to participate. Sorry, it's been a bit long, but I think that I wanted to get you this feeling that there are really unique opportunities in this project that touch a wide range of things, from industry to education, opportunities for young people and opportunities for companies. And that Slovenia, as an owner of the laboratory, and having actually spent resources in building the laboratory, should now look at really how to best harvest and profit from the investment made, trying to get as much out of the laboratory. And we would be delighted if this happens with an extension of our collaboration in the years to come. Thank you. And then I let Joerg continue and tell you how we are doing in building.
So just let's check before I start. The logistic, is the microphone on so that or do I have to switch it on somehow?
It should be switched on, but it's on. Okay.
So it's fine, it will work. So very good. And also one question to the rules. As a speaker, I have to speak with mask, or as a speaker, I can take off the mask. How's the rule?
You can
Okay.
take it off.
Yeah. Okay.
And
Fine.
if you have problems with the pointer, there is another one.
Perfect.
So will you be able to finish in half an hour?
Yeah.
Okay, great.
Okay. That's okay. Yeah, fair. The universe in the lab. So for me, it's a pleasure to present here the status of the realization. You have just seen from Professor Giubellino a very exciting presentation of the scientific part. And I would like to show you now how we move forward in realizing this large-scale project so that you can actually do all the science in this large-scale facility. And here you have a nice overall picture from the area. I think you have seen this image. This here is the existing GSI, 50 years or more than 50 years, in the meantime young. And here the large area of the FAIR project under realization. And it is a real unique facility, what we are doing there. And it also triples. To give you a feeling here, in future there will be more than 3,000 scientists rotating, working on the campus. So it triples the number of people. Currently we have roughly 1,000 people per year rotating and working on scientific aspects. In future 3 times more. So that should just give you a feeling of the dimension which is changing. And that means also that we have to change many things on our campus. And therefore it's important, as this is a long process to realize this dimension, that we are focusing on 4 strategic objectives. Of course, we are realizing the FAIR project in the field. This is what I have just shown, and I will go in more details. The second very important point is it takes time to realize this dimension. Therefore, what just Professor Giubellino presented, to have a continuous program FAIR Phase 0 with the existing facilities, to have all the scientific collaborations active, developing further, and even testing components for the FAIR facility is absolutely important. That's another second strategic objective. The third strategic objective is simply the point you just noticed. FAIR is new, JSI is 50 years young. So the existing accelerator facility has to be upgraded and modernized in parallel, so that together this whole accelerator complex is on the state-of-the-art technology. That's the third program what we are doing in parallel. And of course the fourth program is for all the people who are coming. We need an infrastructure on the JSI FAIR campus which is expanded, since with more scientists, with more laboratories which we need for all the researchers, we have to expand and to modernize the existing campus. So we are building currently a large control center, a 5-story building. The ones who have been at JSI, when you enter the facility, JSI, you find on the right side, after the entrance in the moment, a large excavation where a 5-level building is under construction with 200 office space positions and a large control room, which finally will be used to operate the whole accelerator complex from one location. So it's important to understand we are focusing with all our activities on these 4 strategic objectives to make sure that all this converges properly in line of our realization, to give the scientific groups and teams an excellent research location, well interconnected to the global communities. We have, of course, as you have seen here, numerous collaborations, as touched on by Mr. Giubellino, many people from all over the world. And we have here all the shareholders with different shares. Germany is the biggest shareholder with 70%, and all the other international shareholders in the range of 30%. Russia, currently, as mentioned, a specific topic, but we are addressing that to find solutions, to bridge, to overcome some components which have to come from there, or find other solutions. From the dimension of this roughly 3 to 4 billion euro investment, only FAIR is a 3 to 4 billion euro investment. You can imagine that communication integration is a key factor to make sure that all these strategic objectives, the coordination between the various shareholders, and ensuring that all the deliveries from the various shareholders, and most important, the people are there. I just would like to highlight, beside all what we do, people is the key. Finally, everything what we do relies on competent, qualified, motivated people. And therefore, we have a wide range of opportunities for everybody, since we have all fields. We have the scientific area, but we have for all technical, so engineering disciplines, huge groups on our campus who ensure that this facility can be operated, this facility is maintained, this facility is more developed to the state of the art, and so on. So a great opportunity which finally relies on right and motivated people, where of course you are an important part of. What we are building here, as already said, is we have the existing facility and we have here the new facility. Just for your orientation, later on I show a number of pictures from the construction site where we are. This is here the large ring accelerator, which has a circumference of roughly 1.1 kilometers, 1,100 meters, but it's buried in the ground. So the lowest part roughly minus 80 meters. So in the meantime, it's realized and already covered. Later on you will see that. So that's a very important tool. Then we have here a very important central point. It's kind of transfer section. There were 3-4 beam lines from various angles crossing each other. And this is a very complex building from minus 20 meters to plus 20 meters. And then we go here into the superfragment separator with a very complex building structure where finally the beam is being divided into various sections and finally fed to the various targets, which is under construction. Here is a so-called collector ring, and here is the ion energy storage ring. And here you see adjacent to the existing structure here the proton Linac accelerator, which is under development from a team on our campus, of course, in collaboration with the other communities. Technology is key. I think we are using superconducting magnets, since with the dimension we have the magnetic field to keep the beam on the right position, on the right line. It is important to have very fast ramping magnets, or many fast ramping magnets. Secondly, with a field, you need to have the ability to use power 13,000, 15,000, 18,000 ampere through cables. If you want to do that by the ambient temperature, you would have cables of this dimension, which is simply not manageable, and you cannot build a magnet like this. This is a dipole magnet with cables of this dimension. It's simply not possible. So superconducting magnets means we are cooling the cables, and this is a cable what I'm talking about, with helium to minus 269 degrees. So inside this small cable, it has 2 centimeters diameter, is a small tube where helium is inside, cooling this copper outside to minus 269 degrees. And by that, it is a superconducting cable, and by that we can have 13,000, 18,000 ampere going through this cable and creating the field. So that's what we are doing here. By the way, these are of these dipoles, 100-ton magnets. They are all built. They are all tested. So they are now on our premises nearby in a warehouse waiting for installation. And this is what we are doing with all components. And of course, I think we have to have situations or environment where we are close to the to space, so ultra-high vacuum. Inside of this magnet, there's a small tube, I think this dimension, which has this ultra-high vacuum going through the entire accelerator, and there the beam is controlled on his way to the target. And we are procuring worldwide the component. Just you can see here, that is a fair layout here with high energy beam transport lines where we transport the beam. You can see here dipole magnets which are already manufactured and also in storage space. Then we have here the large ZIS-100 ring accelerator, deeply buried in the ground. Just to give you a feeling, a magnet has to be fed with power by a power converter. We have roughly 800 power converters, which are manufactured in India. So in Hyderabad, in the middle of India, all these power converters are under manufacturing. I think roughly 200 are already delivered. You will see it later on some pictures. And this is extensive work with a partner there to develop this over many years so that finally we have the product what we need. Then we have here dipole magnets, quadrupole magnets here. Then we have here the vacuum chambers where the beam is going through. Of course, they have to be cooled. This is a very special design. Then we have here dipole magnets, which you have just seen. Here, in the superfragment separator, there are large magnets manufactured in Italy from the company ASG, which are also superconducting, numerous of them, and to ensure that finally we have the quality, each magnet is being tested. So each magnet is being tested, so it's manufactured in the location, then brought to a test stand, which we have developed together with the TERN colleagues. And there each magnet is tested in certain conditions, and from there it's transported to our storage area, and when we are able to install, we bring it to the field and install it. So that is running very well. This is the collector ring coming from Novosibirsk in Russia, where we currently have as addressed some topics which we need to solve. Here are for the HESR, the high energy storage ring, dipole magnets, quadrupole magnets, which are already manufactured. I think end of this year we have all magnets together, and after some testing they will be then 100% complete. And here is a proton linear, the proton linear accelerator, which is complex structure, which is completely new. There is nothing like that existing. So it's a development program which is going nicely on. And here you see a prototype for a certain section. And here you see a snapshot from our storage area, which we have rented. Here are these dipole magnets, the 110. Here are power converters. Here are other components, and here are dipole magnets and other components for the HESR, for example. So there's a lot of material flowing, and while we are executing the construction, civil works, buildings with concrete and all what is needed for that, we are procuring all the components, and to start then next year with the installation of first accelerator components. That's the plan. Slovenia is an important part of that. Slovenia owes 1% of all this as a share. Remember, shareholders, they own part of the facility. And there's quite some investment. You find here 2005. I think that's a contractual topic to have an equal way of comparing. It's a calculation based on 2005 numbers. So if you want to translate to today, you have 1.5, 1.6, 1.7 to multiply this number, then you are in real money. And out of that, if you put all that together, what is coming either in cash or through components and investment, we are in this 3 to 4 billion euro total investment. And of course, from Slovenia, there are various components for the proton linear, ZIS-100, HEPT, high energy beam transport, HESR, and CR. Many small components in various fields coming, which are of course vital to operate the facility. Since, as you know, I think magnets is big and impressive, but the magnet itself doesn't help if you don't have controls, if you don't have the instrumentation, if you don't have the control system to operate this in a way. And then we have here, I think, the consortium Technodrome, which is mainly doing this, which is from Instrumentation Technologies and COSI-Lab, where these components are coming from and are already manufactured and delivered, and there is an intensive and close collaboration between all the people. These are further components for various areas. You see PLCs, control units, data acquisition, some boards for data exchange, drivers, stepper motors. So there are numerous components which are already procured or other manufacturing with our partners here, and I think we are looking for more. We are looking also further. I think one is that we have delivery of components. We are now heavily talking with all shareholders. When we move into installation, we need also people who are interested to install, to commission, to work on that. And I think that's also for the entire community of great interest to get this experience, how to bring this facility in operation and to get on the components which have been produced, further experience. How can we develop further? How to advance or how to modify in some areas. So that's a very important step. And thanks to the colleagues here from Slovenia, there's a great and very well-established collaboration, and we are looking for more. Another example, just we talk about control system. The control system is with a large group of people in our controls team under programming. So the control system is already partially applied to the existing facility so that we can learn with that and learn about bugs and further developments, which is normal. But of course, we need to be more efficient in future also, since we need artificial intelligence in the system to ensure that in the most efficient way we can operate with a limited number of operators. We cannot all, like in history, tune by hand the nice knobs and so on. This must be in this dimension be different. So artificial intelligence and working there close together with other partners is very important to bring this into the system. Now moving a little bit to the execution on the civil side. So I think naturally everything is big. So we have here, we're moving about 2 million cubic meters of earth, 1 million out, and of course it is refilled again. So we don't dispose any soil since the whole area is reshaped. Also, before it was a flat area, after that is a fairly hilly area, since the earth is part of the radio protection structure, of course, also. We have a lot of concrete, I think 600,000 cubic meters. We just have a feeling 8 times of a football stadium as a comparison. So it's big and a lot. So we have in the area, in the northern area, wall thicknesses in terms of concrete 2 to 3 meters. In the other area, we have up to 8 meters concrete walls. So that is also from the civil works a special challenge to do that in the right quality, in the right way. And of course, there's a lot of reinforcement steel, 65,000 tons, which we implement in all this concrete. And that is going on very nicely. Here you see a picture to the northern part. This is the ZIS 100 ring, but as you see, you don't see it, since it's underground. So the top of the ZIS 100 ring is roughly -8, -9 meters below the ground level. And we completed the ZIS 100 tunnel last year in May. So it's a tunnel which consists of 2 tunnels. There's an inner and an outer tunnel. In the outer tunnel, later on, the accelerator with all the magnets will be installed. And in the inner part of the tunnel, there will be all the components like power converters and all these materials who are necessary to operate that. And it has to be split, since in the operation there will be some radiation. So we have to ensure that on one hand we can access through the inner tunnel during operation certain areas. Secondly, we also have to protect certain components. They are not used to be exposed to radiation. So therefore we have this inner and outer tunnel, and in between is a large shielding area to ensure that it works. So that's very nicely progressing. All this is now mostly refilled. I think in this month we complete that. And we use now this area. There are new companies, since after finishing the concrete, we have to coat inside the tunnel, and we have to ensure that all these materials which heating, ventilation, electrical, everything what you need to make it operational has to be installed, what we are starting this year. So it's all contracted, we do that. Here you see the transfer, central building. Moving to the next side, this is a central part what I'm talking about. This building here is at roughly plus 20 meters, and it is still progressive since this building will grow across this ones to this side. So it's like a bridge over the other buildings. Here you see completed now in terms of concrete, the building where the cryogenic facilities will be installed. So helium for cooling is a very important part. And company Linde will install there one of the largest cryogenic facilities in these halls. And here you see the tunnel in this direction to GSI, as GSI is in the meantime connected. So here's GSI, the existing, this 18 tunnel. This is a tunnel from GSI, connection here, transfer beam line to the transfer building, this crossing section of various beam lines, and here then the ZIS 100 tunnel. And then it goes here to the southern area with many buildings also there under construction. And this is the southern area. Here the beam is coming. There's another building in between growing. This is just started. And here is a large experimental area in the southern area. Here APPA will be. Here will be the superfragment separator. So the NUSTAR teams will be very heavily working here in future. And it is well under construction. And when this is concrete-wise, further progress, then of course we start with the installation of all this technical building installation activities, heating, ventilation, cabling, and so on. That's a look inside in some areas. So in this transfer section, but I show you a much better one. This is now the tunnel inside. I think where the tunnel is, the ZIS 100 is in certain sections coated in the meantime, dust-free and with the right condition, what we need for all the magnets. So in here, we will now start next year to install first magnets step by step and install the accelerator. And of course, this year we start to install there the electrical systems, ventilation, and so on. Yeah, this is basically the overview again. You have seen this transfer section, the ZIS 100 tunnel, including an inside that is coated. This is this famous bridge where you have seen only this section. This will grow up here. And you can see that the whole area will be fairly hilly. And all the roofs are not normal roofs. I think they are all covered with green environmental friendly plants and so on, so that it is a nice area. And then we have here this building section which I have just shown. Here is this upper area. What I have seen here is superfragment separator, the NUSTAR area, which is under construction. Here is the collectoring, and here in the future the HESR. Some images, I think our logo, the universe in the lab. This is a way if you in future, if you do some studying or visit or work for some time on campus, you can walk this area and see this kind of images when you walk the fair area. This is the proton LINAC area, which you can see. This is another section, how it will look like. All that relies, and that is important, finally, on people who are contributing, competent, and qualified. And that ends with my session. Thank you very much.
Okay. I would like to thank both speakers for very interesting and informative presentations. Now we have something like 5 minutes for the questions. So please just go on. If there's some question, just raise the hand. Okay.
I have a simple question. You have mentioned the radiation shielding between the outer tunnel and the inner tunnel. So my question is, will it be used only to protect the equipment, or also the people working there during the experiment? And another question, what are the dose rates which are expected in the tunnel, and by what factor will it be reduced by this radiation shielding?
Yeah. So of course, as I said, people is the key. So I think, of course, naturally the answer is clear. I think people have to be protected such that nobody is in danger. Absolutely clear. I think that's fundamental. Just from the overall, all these facilities are under permits. So there is an approval process for permits, how you can approve this to build these facilities. I think. So all this is calculated and done as per the latest law and regulations. I could not, out of the top of my head, say you the exact dose rate. I really have to go to my people there to ask what is in which area. But it is such that people can walk the inner tunnel, since that is one prerequisite, so that during operation we can, in case there's an issue, some technical topic, people can move into that. Secondly, as all facilities like that, there's an access control system, which is under development. We have prototypes for that, so that only people can enter this area if it is secure and approved and checked that there is no risk for any person. Yes, a monitoring system. I think there's a monitoring system, but also there are these gates which where you can only open. I think we have these hand vein scanners now. You put your hand there, then you are identified as a person. And then if the system is such from the stage that you can enter, you are allowed to enter. Without that, you cannot enter. So people protection, of course, is the absolutely key, since finally we want to be successful in science.
Maybe one small point there, if we go back to any of the pictures of the facility, one thing which is special about this, that has a lot of impact on the type of controls, here, is that we actually have the upper part, all of this area is a public park. So the radiation levels are not like in most physics laboratories set for employees that, have categorized as somehow risk workers, but is for general public. So that is much more stringent because people have to be able to go walk and pick up mushrooms in the woods here without danger. And that sets our limits much lower than what normally you have in physics laboratories, because it's not the employee levels, these are general public levels, which are much different. So,
okay, thank you.
It's a very safe place by construction, because people have to be able to go walk with their stroller.
Some other questions? Huh?
So connecting directly to the public park issue, we can see there's a pond planned in the middle of the facility. Is that for fish only, or would we be able to swim during the night shifts? And
Neither.
No, it's not. That is for cooling purpose and other purposes. That's not for public. And the public area is this part. This one will not be public like that, since there we have all the experience. Here in the northern part, we have only 3, and one is here, entrance areas to the tunnel to really go down. This is then nicely fenced, controlled, so then these areas around can be normally used. But in the southern area, I think this will be more restrictive for public use, since we have much more access doors and much more also movement of people and scientists and technical people.
thank you.
Yeah.
Okay. The last question, probably, because we are tight in time. Maybe I have a short question. When you presented these medical applications in the beginning,
Yes.
how long does it usually take from this research stage to the point when it can be applied in practice?
Oh, it a lot depends on the pressure there is for each application. But for example, the therapy took a few years. The new type of therapy that are being studied, for example, flash, this very high dose in short time, first applications to humans will be almost immediately, 1-2 years afterwards, because it's already in a framework of it's a new use of something which is existing. But of course, there's all the regulatory part and so on. The way this type of therapies start is always for a subcategory of patients for which there's no other possibility, and therefore they are aware of this and they try an experimental therapy. So it is not meant for general application, but for cases in which there's no choice. So that is where we start, and then it goes into, for example, the treatment of the heart is in this phase now. If someone has no other way to resolve the problem, then is entitled to try in this way. If there's other possibilities at the moment, you don't do it. And it will take a few years then you accumulate cases, and then you go through the approvals, and it's always a rather lengthy procedure. But there is this life-saving situation in which there's no other possibility to save a life. You try and you consciously and you therapy, and that is where, for example, the heart therapy is at the moment.
Okay, thank you. I would just like to explain something to you. This is not the whole audience that participated today. We had quite a bit more online, so this is a wrong image of the popularity of your talk. So I would like to thank you again. Yeah, it was really nice to listen to both of you. So maybe we should thank.
Thank you very much.